So we're going to be interpreting and sketching graphs today. This is day 4. And this graph here is going to show the depth of a scuba diver as a function of time. Depth. So here I have Batman on the whiteboard. And there's no chance I can get this off. So I just want to have Batman here on the whiteboard. If you're following along at home on the YouTube, you can't see this, but I'm going to pretend that Batman, this is 0 depth, okay? Because he's on the surface of the water. So if you had a timer, or clock or something, you would start the timer, right? And time would move on in this axis. Typically, x-axis is used for time. So for example, in the first 4 minutes, click your stopwatch, time goes on for 4 minutes. How far does our friend here, Mr. Batman, how far does he get? Excuse me? In the first 4 minutes, he gets 12 meters. So what happens to Mr. Batman here? He goes down a distance of 12 meters. Okay? And that took 4 minutes. Now, how many are in Science 10? You've taken the physics unit. What do you guys know about a distance time graph for a straight line? What kind of motion is that? What kind of motion is that? Uniform motion. Good. So, our friend Mr. Batman here, he traveled those 12 meters in a constant velocity. Do you remember we were talking about slope in the past few days and how this is a constant rate of change? So it's like, how much is it over and how much is it up? How much is it over and how much is it up? If I zoom in, is it a little bit easier to see? It goes over 1, and then how much does it go up by? 3. And then you make this staircase. Can you guys make this staircase with me? Over 1 and up 3. So what is that constant rate of change there? In 1 minute, yeah, in 1 minute here, he goes 6 meters. So how far could you go in 2 minutes? Divide both of these by 2, and you go 6 meters in 2 minutes. So I screwed up right here. This is a 2. It's one unit over on the graph, but each unit over represents 2. You guys see how 1 increment is worth 2? 2, 4, 6, 8. Okay, so in 2 minutes, he was able to travel 6 meters. So how far could you go in 1 minute? Divide by 2 again, because it's all just a nice ratio. You can go 3 meters in 1 minute. So what would be the rate? You know how you do like kilometers per hour for your rate of speed? It's distance on top and time on the bottom. So you would go 3 meters per minute. That's your speed. 3 meters per minute for that first interval. Okay, so in the first 4 minutes you travel 12 meters. What's happening in the next 4 minutes between 4 and 8? What's happening here where the depth doesn't change? So what's he doing here for 4 minutes? Does he go up or down? So for 4 minutes, he's just hanging out here at 12 meters. Because what's not changing? Yeah, the meters is not changing. So right there, you want to say at rest. Some of you probably recognize that from Science 10, right? Okay. Now what's going to happen for the next 4 minutes, from 8 minutes to 12 minutes? What's going to happen to Batman here? He goes from 12 meters of depth to 20. So this was a distance of 12. So let's make it a little bit smaller, to 20 meters. So then Batman's now here in the same 4 minutes. So for this interval here, how far did he travel for this interval? Look at this triangle I make. You guys see it? How much does the x change and how much does the y change? Come on, yell it out. Don't be afraid. How much does the x change in that little triangle that I made? It's actually only 2 minutes. Did I say 4? It's only 2 minutes, from 8 to 10. So you sketch this one in. That's only 2 minutes. How far did he change in the y? 8 what? 8 meters. So now look at this ratio. 8 meters in 2 minutes. Jot that one off to the side. 8 meters in 2 minutes. Could you do a division there? What's 8 divided by 2? Good. So he goes 4 meters in 1 minute. So that would be a speed, a rate. That's the key word here, rate. Rate of speed. And you would say 4 meters per minute. See how I use the word per? 4 meters per minute. What was the speed before that? In the first interval. He was going 3 meters in a minute. So which one was faster, this first interval or this second interval? The second one's faster? And I don't know if you can see this, but what that means is this line right here should be a little bit steeper than that line. I don't know if you can see it because it's really close, but this one should be a little bit steeper. Okay, now what happens for the flat part? At rest again, very nice. And for how long? Two increments, so good, 4 minutes. Now here comes the interesting part. This last piece, what's happening to the depth? You go from 20 all the way to 0. So which way does my friend Mr. Batman go? Which way does Batman go? Back up. Okay. So he's actually losing depth. If you're losing depth, you're traveling up. If you're gaining depth, you're traveling down. Good. My thing's all screwed up. With me, guys, draw the triangle that goes with this last section. So you'd have to draw a line that goes from there to there, and a line that goes from there to there. In science, they would call this delta y, and this one they would call delta x. In math, we call delta y the rise, and delta x we call the run. And we like to keep it in a ratio, because if it's a straight line, that ratio is always the same, whether you use, could we count this up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 increments on the graph. What's each increment worth? 2. So how much depth did we lose? Negative 20, in a sense. We lost 20 meters of depth, which means Batman went up. When depth is positive, Batman went down. So that's what positive and negative means for these graphs. It's like direction. Which way are you going? Like in Science 10, east and west, you have like positive and negative. Okay, what about delta x? Count the ticks. How many ticks? 1, 2, 3, 4, 5, 6, 7, 8. And each tick's worth 2 minutes. 8 times 2, 16 minutes. So for that one, we would have negative 20 meters in 16 minutes. See this ratio? Could we reduce that ratio to like a lower terms fraction? What do they both divide by? A better one than 2? 4. So divide each by 4, and you get negative 5 over 4 meters per minute, which if you went to a decimal, 1.25 meters every minute. So that first slope was 3 meters per minute. This slope was 4 meters per minute, and this slope was 1.25 meters per minute in the opposite direction. So which one was the fastest? The 4 meters per minute, the middle one, right? The second fastest is the 3 meters per minute, and the slowest was the 1.25 meters per minute. And when you're talking about speed, how fast, it doesn't matter the direction. Like, don't think about the positive and the negative, just think about the numerical value. And if you were to look at steepness, is this line steeper than that line? So that's why you're going faster here. So it's all about steepness. So I'll just draw this on the whiteboard. If it takes a whole bunch of time to cover a little bit of distance, a huge amount of time, and you just cover a little bit of distance, are you going very fast? Not very fast at all, right? Is this line very steep? No. But if you did like a really short time frame and you covered a whole bunch of distance, how fast are you going? A lot faster. You see how steepness on a distance time graph will indicate how fast you're going? Okay? Lots of distance in a short amount of time. Not a lot of distance in a long amount of time. That's speed. That's rate of change. Okay, let's answer some of these questions. Some of these easier questions. How long did the dive last? 28 minutes? That's not too bad, right? You just look horizontally. Oh, my bad. Thank you. And at what times did the diver stop her descent? Well, Batman stopped a couple times, right? At what times? 4 minutes and 10 minutes. So 2 answers there. And what was the greatest depth reached? So the greatest depth, you would have to look at the highest value on the y-axis. So 20 is the greatest depth. That's as far as Batman got. So 20 meters was the greatest depth. And for how many minutes was the diver at that depth? Right here you look, how long was he at that depth for? 20 meters for 4 minutes. All right, so basically what we're talking about here, guys, is the properties of a graph can provide information about a given situation. Lots of the time, you guys, especially in Math 10, Science 10, you're going to get distance time graphs. And if you see linear, this right here, if you see linear, you're talking about, in physics, they would call it uniform motion. That's what they call it in physics. It basically means you have a constant, what? Good, constant speed. You're not what? You're not, it starts with an A. Yeah, you're not accelerating, good. If it's curved, then it's accelerated motion. And accelerated motion, I mean, if the first one was called uniform, what do you think the next one's called? Non-uniform. Okay, and then the last one, when it's flat, you are at rest. And that's for, these are for distance time graphs. What the book here has is just in general, because they're talking about rate of change. It doesn't have to be distance and time. It could be like money versus time. Think about like how much you get paid, dollars per hour. Maybe Maybe every hour you work, you get paid more or something like this. Okay? So it doesn't have to be money, or it doesn't have to be distance time. It could be anything. And then also they talk about the steepness in this picture here. Okay, moving on. So that last graph we did, that was continuous. That was a continuous example. This graph here is an example of discrete. All right? So what is the independent and the dependent variables? Does cost depend on mass, or does mass depend on cost? Good. So it's a cost versus mass. It's always like that, y versus x. So cost depends on mass. I'm assuming the more mass you have, the more pricey it's going to be. I haven't even read it yet. It looks like it's popcorn. I mean, if you buy more popcorn, do you think it's going to cost more? It's like small versus medium versus large. So which bag's the most expensive? C. And for some reason it has less mass than D and E, so that's bizarre. Maybe there's a deal on C or something, I'm not sure. This is weird. Which bag is the most expensive? C. And what does it cost? You would have to go and find C horizontally and then find C vertically. And then also being able to read the scale is a huge skill. So like look vertically, in 2 ticks you get to 2. So each one's worth 1. 1, 2, 3, 4, 5, 6. This is $7. So $7. Which bag has the least mass? So mass is horizontally, so least would be closer to the origin. Okay, so B. Least mass is B, and how much mass does B have? Looks like halfway. So if this one's 400 and this one's 800, what's this one in between? 6, so then you could go half of 6 and 4, that is 5. Good. So 500, and the units are grams. I really recommend that, especially during the exam, like, and when you're doing your homework and stuff, and the quizzes, it helps to put the units. Do not be lazy with the units. They actually help. Okay, which bags have the same mass? D and E, you can look like vertically here. They line up vertically. So that must mean they have the same mass right there, which is what? In between 16 and 20? What's in between 16 and 20 halfway? 18, good. So 1,800 grams. Which bags cost the same? Cost is a vertical axis, so you actually look horizontally. Okay, so hopefully you start to see that. So for the vertical axis, you're looking for something that lines up horizontally. A and E, and that cost would be $4. Okay, AE, $4. And which of the bags, C or D, has the better value for the money? Better value would mean you get a better bang for your buck. So you get the most stuff for the least cost. E, very nice. It takes a while to think it out like that, right? Oh, well, maybe we think outside the box. You guys feel like rebels today? Let's put E. You guys feeling like that today? It's Friday. Oh. Yeah, okay. Between C or D, I would pick D, right? You're getting more popcorn for less money. You could jot that down. More popcorn, less money. And if like if the popcorn in D is the same popcorn in C, wouldn't you rather have D? Obviously. Okay. Let's jump to the bottom here. Oh, this is the most fun. Describe the journey. You get to be creative. Maybe. Yeah, there's one quiz question that you'll see is like this. All right. Okay, so imagine you had a stopwatch in your hand. Okay? Hit the stopwatch. What happens in the first hour? What happens in the first hour? So about 60 meters traveled. Kilometers, thanks. About 60 kilometers traveled in 1 hour. And what would you say about the rate of change? Is it uniform motion or non-uniform? Is it constant velocity or accelerated motion? Okay. At a constant speed, because you keep traveling the same, it's like a staircase. You travel the same amount of time, the same amount of distance in the same amount of time. Then what happens from A to B? Okay, I heard someone say you pause, which is a good word. Take a break. That's like sort of the everyday language, right? Take a break, have lunch, maybe get some gas for your car, whatever this guy's doing. So he's taking a break. So he's at rest. For how long? Someone's about a quarter of an hour, he looks like. Very nice. About 15 minutes. Do you guys see how it's about half of a, if that's one increment, it's half of that increment? And one increment is a half hour. So half of a half, 15 minutes. Then what happens from B to C? B to C. Sure, constant velocity or constant speed. And then you could even give a distance, like for like about 60 meters to what? About 130? In how long? 45 minutes? No, longer than, oh yeah, 45? Yeah, good. The rest of that hour, good. In about 45 minutes. Yeah, C to D, longer break. Longer break. And then this is the weird one. D to E. Good. Are you in Science 10? No. So the way to think about this, and like I don't like the fact that they use this word distance here. What should this actually be? Because a distance graph wouldn't come back to home. If you're in Science 10, you know distances don't go back to zero. Displacements do. So from D to E, it's like returning. Return to origin at constant speed. You guys feel okay about this so far? And sorry about the people watching the video. We did this on the whiteboard. Okay, let's read this quickly. Samuel went on a bicycle ride. He accelerates until he reaches a speed of 20 kilometers an hour. Because you have to start at zero speed, right? You hop on your bike, you have zero speed, you start pedaling, and he gets up to 20 kilometers an hour. And then he holds that speed, magically, for 30 minutes. Okay? So let's start there. What are we putting vertically? Speed. And the unit for speed will be kilometers per hour. And what are we going to put horizontally? Time. And that unit will be, it looks like, I wonder if minutes would be easier. because they're giving us this stuff in minutes. All right, now we need to think about like what these scales are going to look like. So what's the maximum speed he gets to? 20. And then he gets to a hill and his speed decreases, so it drops. So we only need to get up to 20. So what kind of a scale do we want to fill this graph? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So doing ones is not going to help us. Do twos. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I guess the idea is you want to fill the graph. You want to fill as much as possible. You don't want to have like your graph just in the bottom little corner there. Yeah, that's all. And then how much time? We've got 30 minutes and then what? Another 10 minutes and then another 10 minutes. So we got to get to at least 50 minutes. So what do you want to go by? 5s maybe? So 0's in the corner and then go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay, we did our best to fill the graph. All right, so I'm just going to zoom in on the graph. I'm just reading the page here. Sam goes on a bike ride. He accelerates until he reaches a speed of 20 kilometers, and then he cycles for 30 minutes at approximately 20 kilometers per hour. So all you have to do is draw a line. You don't have to worry about the acceleration part. You just draw a line at 20 kilometers per hour for how long? 30 minutes. That's all you have to do. So the question is, how did he get from 0 to 20 in no time at all? So it's just, it's an oversight. You're ignoring that initial acceleration. It's a bit of an oversight. Okay, and then what? Then he arrives at a hill, and his speed decreases to approximately 5 kilometers an hour for 10 minutes. So now you're at 5 kilometers an hour for 10 minutes. How do you guys feel about that one? How do you go from 20 kilometers an hour to 5 kilometers an hour in no time at all? It's just an oversight. We're just ignoring that. We're ignoring the accelerations. Because it's constant speed for 20 minutes, and then it's another constant speed for 10 minutes. What should there be? There should be a line that's connecting here to here. Okay? And then the very last part, he stops at the top of the hill for 10 minutes. So now what's his speed for 10 minutes? Nothing. Okay? So this would be a speed time graph for constant motion. Or for uniform motion. So like uniform motion, is your speed changing? No. That's why these graphs are flat. The only thing we're missing is the connecting points, which we can ignore. All right, so this one here, you're just going to grab a partner and you're going to discuss the 4 situations and see if you can match them to the graphs. Then we'll talk about them. Yeah. Easy? Okay, I think A is an easy one, right? Which one's A? The vertical growth of a tree? It's good. So I think for A, you'd have like a height versus time. And you can see how I use my pointer. As time goes on, the tree gains height. Okay, so that one's not too bad. That one's B. Okay. How about graph D? I think graph D was the next one that was easiest for me. I had this one for A. Think about the height versus time. So you'd have to start, I heard Jamila say this, you have to start from a high position, right? And then you jump, and you lose a whole bunch of height. But then those bungee cords snap tight on your ankles, and then it snaps you back up, right? So then you rise again, and then you fall again, you rise again, and you fall again. Or it just snaps and you die. That's kind of crazy. Okay, so we got A and B taken care of. Now, the next one that was easy for me, easier in a sense, was the temperature of the hot chocolate. Because if this was temperature, capital T, and this was lowercase t time, just listen up for a sec, guys. As time goes on, what happens to the hot chocolate? Yeah, it cools down. Yeah, losing energy to the surrounding system. All right. So that one is C. Now, can I just get you guys to stop talking for a sec? Thanks. Now, for Calgary's temperature, for the daily average, that's what that says, daily average. So this is temperature versus time. In the morning, maybe this is 12 a.m. This is midnight. You're thinking Calgary, so you're thinking like, okay, it's just like Edmonton. It's kind of cold if it's winter, especially. It's below 0, and then maybe it's a hot day. This would be like 12 p.m. So this is noon, and you get like a daily high because the sun is shining. And then it's 12 a.m. again, the day has elapsed, and it's cold again. It's not exactly the same temperature as it was to start the day, but 24 hours later, it's cold again. Cool enough? All right, so you're going to take care of this weekend? Okay, this weekend, because we're moving on to the next lesson.